All right, I am so excited. All right, so I know we were thinking about moving from Bootstrap to Tailwind, but you probably saw on Twitter that I pivoted and we're going to start our JavaScript journey today. And the reason for it is that the more I looked at Tailwind, which is awesome, the biggest value of Tailwind comes from when you actually have a pretty robust or strong JavaScript presence in a front-end web application. And so what I really want to do is keep to our intention of first learning the core language features of JavaScript as themselves, as a programming language, and then looking at, okay, how do we use that language first in the browser and in the back end? So what we'll do is we'll learn those core fundamentals of JavaScript, and then we'll look at what it means to operate that language in the browser, and then we'll pull in Tailwind, and you'll see some of that value. Then we'll shift over to the back end and look at what it means to use JavaScript on that back end server kind of computer programming. But what's cool is tonight we're actually going to do the first computer programming that we've done in our programming school, because we're going to learn a real language. Now, I think that every one of you has already had some exposure to JavaScript. Is there anybody that hasn't done some JavaScript work already? Okay.
I have, but just it's very limited what I've done. I'm very almost brand new with JavaScript.
Okay. What programming languages have you touched already, Jason? I almost called you Jason. What's your name?
Well, when I was a teenager, Pascal.
Wow.
QBasic. No, Python a little bit, but not too much.
Okay, good. All right. So here's how we're going to approach this. The first little bit I'm going to go over with you is, what are the core elements of every single computer programming language, no matter what language it is? I've already mentioned these 5 things, but we're going to expand on them a little bit. And then we're going to look at how is each of those implemented in JavaScript. So the first part really is your blueprint for how do I approach learning any new language? And this is the exact approach I use when I look at any new language, even now, right? Because I learned these fundamentals years ago, and until the actual underlying paradigm of how a digital computer changes decades from now, if ever, this is going to be true for all computer languages. So the first part of today will just be a little bit of lecture. It won't be that long, honestly. And then we're going to switch over and we're going to dive into actual coding, where we're going to look at those 5 things. I'm going to be demonstrating them live, and you'll follow along inside your code editor and see each of those things as they work out. Some of this you will have already learned. Some will be new to you, but besides the JavaScript part of it, I really want you to think of this blueprint of what are the 5 basic elements of any computer programming language. And as I approach studying something new in the future, I want to keep these in mind and look at how a language does these things. So I'm going to share my screen and we'll just start looking at some stuff here. And as always, interrupt me at any point. All right. I'm going to just make a new text file here, because I'm just going to be writing down some notes, and I'll give these notes to you as well. So we've talked about these 5 basic elements of any program before. Does anybody remember what they are?
Start.
Input and output. Are those
Entrance or start point. Good.
Variables.
Variables. Now, just a moment. Jason, you were saying something.
Oh, I said input and output, but I don't know if I'm thinking of the right thing. You went over this before. I know you've talked about it.
You're on the right track. When we look at the basic purpose of a computer, its job is to take in data, process the data, and then send it on. But this is exactly related, Jason, because that middle part of processing the data uses these 5 things. In fact, one of the things I'm going to do is I'm going to save this file, and we'll put it in just documents. Actually, no, I have a 5Live site here, and I'm going to call this is not going to be a text. It's going to be marked down because it'll be a lot more friendly there. All right, good. 5 basic elements of any program. So yeah, an entrance or starting point, variables. What's the next thing? Anybody remember? And I know you know these almost by heart. Jonas, anybody else remember?
Branching.
Oh, not you, someone else. Who was that? Was that Jonas that said that, or was that Sudesh?
It's me.
Okay, all right. I want someone else besides you, because you know these so cold. You already said it, so I'll put it in there. Branching or control instructions. I'm not picking on you. It's actually really awesome, Jonas. Someone else besides Jonas remember the last two? It's okay if you don't.
Absolutely don't remember.
I don't remember conditionals.
That's
don't
under
know.
branching and control. That's totally good. All right, it's sub programs.
Uh,
And then 5 is the opposite of number 1.
Exit.
Exit.
Exactly. An exit or ending point. Okay, good. Now, let's explore what these mean, and we'll look at some actual code examples on this. Okay, first, I'm just going to expand on this. I'll do it down here, actually. Let's go. So here's the thing here is programs are a series of consecutive instructions. That's what a program is. Like, let's get down to the rock bottom basics we remember from before. We have a central processing unit, and it has what's called an instruction set. Now, I don't expect you to remember all of this, but I'm just going to ask, does anyone remember what this quote unquote instruction set is?
They are the commands the CPU can perform.
Perfect. Now, how do they get there? Who comes up with these?
CPU manufacturers.
Good. They're literally installed by the manufacturer. And there are typically about a couple of dozen. That's all. That's all. There's just a couple of dozen things. Without remembering specifics on this, what are some of the kinds of things that you can tell a computer to do?
Arithmetic and logical operators.
Arithmetic, logical operations. Ellen, were you saying something?
Yes, I was going to say the logical operation.
Good. Input is one, like taking in digital information. Output. This is deliver digital information. Move data from one location to another. They all revolve around this. What was that?
Load.
I'm missing the word.
Load. L-O-A-D.
Oh, load? Now, like, what do you mean by load? I think you're on the right track. Tell me what you mean by that.
Load means putting one data into a place that we want.
Good, excellent. Yeah, that's a precision. I'm going to call that number line 21, moving data from one location to another. You're totally right. Okay. In fact, load is very close to the actual name of the instruction on most CPUs. That's excellent. These are about it. There's a lot of nuance, but without getting into the actual nerdy, these are in binary form, right? Without getting into the nerdy stuff, let's just look at what needs to happen to add two numbers. So if someone's going to type in one number and then another number, the code to do it would look something like this. Input data from keyboard. Put that data in specific memory location. And then we do this again. And then we do this again. Then we'd tell CPU to add 2 numbers. Give CPU memory location of first number. Then second number. Do math. Store result in accumulator. That's a registry, right? Remember that? Where you put math operations. Send result to another machine, say a display. Now, probably there's even more nuance to it. It's been a long time since I programmed in these binary machine language instructions. But you can see this is just a a consecutive series of instructions. That's all a computer program is. That's all. Now, it can appear like that's not true in certain types of programming, but it's always true. A computer does one thing. And when it's done with that and ready for the next instruction, it does that next thing. And what is it on the CPU that tells it, do the next thing, do the next thing, do the next thing?
Instruction set.
The instruction set is what to do. You have to tell the CPU to actually do a thing. Someone said it. Who was it?
The clock.
Exactly. Every single time the clock does an uptick, sends a signal, the CPU looks in the instruction register and says, what's the next thing I need to do? Well, it's input data from the keyboard. Okay, I did that. Then the clock ticks. What do I have to do? Oh, take that data that I got and put it in a specific memory location. Okay, I did that. And it waits. The clock ticks. Oh, I need to input data again? Okay. Now, an important thing to realize here is that the CPU has no real concept or thought, because computers don't think, of what it did immediately prior. It can only be doing one thing at a time. And again, with the complexity of modern computers, it can look like it's doing multiple things. But it can be doing multiple tasks in parallel. It can only do one part of each of these tasks at one time. So keep that in mind when I say that we need, we're going to kill all of this, okay? Then we need an entrance or starting point. To be very precise, we need the first instruction of the program. Now, after that, the computer will have loaded all of our instructions into RAM, into memory, and they're just sitting there. And it's going to go through them one by one by one. But it needs to know where the first one is. That's what an entrance or starting point is. Any questions about why the computer needs that? Okay, good. So, why is this valuable? Why do I care as an engineer, as a developer? It's going to happen anyway. This isn't something that I ever have to like really designate. It's not like I am so close to the CPU that when I write a program, I'm telling it in what exact memory location the first instruction is going to be. That isn't happening. Why do I care that to know that wherever that instruction is, there's going to be a first instruction? How does that help me? Any thoughts on this? You want to follow the logic in a program that you didn't write, which happens all the time as engineers. We are onboarded to a new project and there's a bunch of work already done. You've got to know where it starts. In very practical terms, one of the reasons it's valuable to think with this is that when you inherit a new project or you're a new contributor on a project, one of the first things that's smart to do is find out for the particular type of computer program it is and the particular language, where in that series of steps will I find the first point that I can stop the program while it's running and just look inside and see what it does, and then step through one instruction at a time. I can't tell you how many times I've inherited a new project where I was just, I knew the language and I kind of knew the kind of project it was, but there was a whole lot going on and I was overwhelmed by the sheer complexity of it. And to start, all I did was use my developer tools to put what's called a breakpoint, a point where the program will stop its execution midstream and just wait for you to tell it what to do next. And I would just look in there and then literally step forward one instruction at a time, watching the variables in the program, watching as it executed controller branching statements, loops, if, then, else, all these things, and start to get a sense of what this program was doing and how it operated. If you put one of those breakpoints way far down the program, because you're not really sure where the program starts, a bunch of stuff has already happened that you're not really tracking very well. And it's much less valuable as an analysis tool. And so this is why it's valuable to know that no matter what, a program has a first instruction. Find out how close to that first instruction can you get to step through the code. There it is. The closer you can get to the first instruction, the better your understanding as you step through the code. All right, questions so far? Okay, good. Excellent. So let's move on to the next one. Variables. First of all, what is a variable?
It's a placeholder.
Explain what you mean, Jonas.
No, it's a container in the memory, which we could put
a container. Go slow. This
in,
is good. This is good. Container. Okay.
In the memory.
Good.
That we could store values in, such as strings, numbers, or other data types.
Good. Okay, so there's one aspect of this that's missing, and it has to do with the name. What does variable mean? Outside of programming, what does variable mean in common English?
Something that changes.
Good. So integrate that concept into what you said. It isn't just that we need a container in the computer's memory where we can store values. What is it about those values?
They can be changed.
They can be changed.
They can be overwritten.
This is the important point. It's that we're storing data that can change as the program executes. Now, here's a question. Why do we need these? It's best answered by considering the question of what would it be like to create programs if we didn't have these.
So that means we would be hard coding every single time we have to enter a new variable.
Exactly. Let's make up a situation that's actually very real. Let's say it's the 60s and you're programming computers. At this stage of our industry, they were giant mainframes. And let's take a very typical thing you were doing. You were writing a program that would calculate how to set up a missile for the military that would fire off, fly a predetermined distance, and land, thereby killing lots of people. It's kind of crappy, but that's what computers were used for in many of those early years. Now, let's say you were doing that for a specific model of missile, and you worked really hard on it along with the team for months, and you designed a computer program that had in it data specific to that exact missile. All of the values for volume of the container that holds the propellant and weight distribution throughout the entire missile, aerodynamic data, anything related to performing those complex calculations was a permanent fixed part of your computer program. Now, for those of you learning programming right now, that sounds really stupid. And from a certain point of view, it is. But that's the way programs were made in early years, all too often. Now you need to do the same project a year later. You need to do the same project a year later with a new, slightly different model of missile. And you have to build an entirely new program to do it. When the fact is, probably 70 to 90% of what your program is doing just needs new values entered. So this is a real, almost like duh thing. But it's important to recognize that without the ability in a computer programming language to have variables, the utility of that language is very limited. But someone has to make the computer language capable of having such things. Early computer languages didn't. There was only constant values that could be entered in. So this is why we need variables. How does this help you? It's the first place to start. In learning a new language. How do I make variables? You have these questions. You have, how do I make them? And then you have, what types of data can I use in making them? What impact on the efficiency of my program will those data types have? These are questions you want to answer about any new programming language. And they all derive from the fact that you're going to have variables. Those variables will be of a certain type. So now we're going to take a little teeny bit of a detour. And I'm going to label it detour off of these 5 things. What is a data type? Anybody want to take a crack at it? Tell me what they think a data type is. Not specific examples. We've already had examples of strings, numbers, etc. What is a data type?
Is it a way to identify what kind of operation or? program we would be able to do with this data. It's all depending on the type they are.
That's beautiful. Yes, that's absolutely a part of it, and it's a key part. So Ellen hit the nail on the head on a key part of it. This would be a simple way to describe a data type. A description of the structure and behavior of a distinct kind of information. So it answers two questions. One, what does it look like? Two, what can it do? Let's take a number as an example. So what does it look like?
A digit or a combination of digits.
Good. Good. What can I do with it?
Arithmetic operations.
Math. Or for those of you in England or Ethiopia, maths. Okay. Yes, good. All right. We're not going to go through all of these, but let's look at strings. So what can I do with it? Oh, no, sorry. What does it look like?
Letters.
Letters.
Good. It is a set. I'm going to capitalize this because a set is a specific term, a collection of consecutive items of alphanumeric characters. That's what strings look like. It's actually really important to understand that. A string is not one thing by itself. It's actually individual things in a row. It's a collection. It's a set. You can even think of it as an array. So that's what it looks like. What can I do with it? Can I do math?
Kind of.
Yeah, but that's a cheat. You can make it work. What do you do with it?
Display characters, read characters. I don't know.
I can read it. I can add characters. I can remove characters. Anybody think of anything else I can do with it? It's just a collection of items. I can read what they are. I can add some characters. I can remove some characters. That's about it, right? Okay, now, this leads us to a really important concept. And this is why we're doing a little detour, because this is going to come up immediately following this discussion of the 5 elements when we start talking about JavaScript. And here's part of the detour again. Detour part 2. What is an object in any programming language?
I'm not sure.
Go ahead. Yeah, Ellen.
But I would say, is it like a collection of variables?
This is very close. That's one part of it, is a collection of variables. Yes, it is a thing tracked by the program that has one appearance and two behavior. In other words, what it looks like and what it does. Let's take an example of an object. We would have,
For instance,
what?
Car.
Good. Yeah. Let's take something we're actually going to see in code all the time. Let's say we have a student. No, we have a class object. A school class, right? What's the appearance? Like, this is what does it look like? This is where Ellen was spot on. These are its properties or variables. What are some examples of the appearance of a school? Its properties. I'm sorry, a class.
Number of students.
Course.
I got number of students in the class. Good. What was the second one?
Course.
Like the name of the course?
Yes.
Good. Excellent. You might have a detailed description that you could use in a catalog. You might have like
Room number.
grades it is suitable for. You might have prerequisites. Any other ideas?
The teacher.
Good, excellent. You might have a teacher if it's only that teaches it. Good, excellent. And there's probably lots more. Now, behavior. So here's an example, and we're going to go a class object. It might have appearance, what it does. And that is some properties. I'm just making this a little more readable. And now let's look at behavior. What does it do? What can you do with a class?
Teaching.
You can start the class. Good. Like the class started, which means you can also end it. The class is over. You can add students to it, right? You can change its name or description. Or the teacher. Let's say a teacher retires mid-teach or mid-instruction. These are all behavior. They're not appearance. This is appearance. This is behavior. This concept is unbelievably important because you're going to see this play out in every single computer programming language in varied ways. What you're seeing up here, to go back to the data type thing, is in order to make our jobs easier as programmers, every language comes with some built-in objects. And These are called native data types. They come with the language.
So are you saying that a data type is an object?
Yep.
Okay.
In the abstract high-level sense that any data type will have both structure and appearance and behavior. From that point of view, it's an object. Now, to be very clear, this word object, many languages take it over and make it mean very specialized, exact things for that language. In some languages, they're not really going to call the native data types that it comes with objects. In some, they are. For example, JavaScript, everything's an object, which is something we're going to get into later today. In other languages, they don't call it that way, but the concept absolutely is the same, and is the same with every language, which is any object. Let's go back down. What is an object? Any object is composed of two parts. What does it look like, and what can it do? Now, the cool part is that in learning a new language, you've only got to master two skills. One, what are these built-in data types? And two, can I make my own objects tailored for my program? Let's say that you need something more than just numbers and strings and Boolean values like true, false, some of the built-in or native types. We're absolutely going to need our own data types. So the answer is, of course, yes. And when you make them, you're going to give them certain properties and certain behavior. Well, let's look at this. When you make these properties for your own objects, you're going to make them in great part by just using the ones that are already there for you. Number of students uses the native type number. Now, your language that you're learning might have several different types of number built-in data. There can be floats, decimals, integers, big integers. There's all sorts of variety in there. But you could have number of students be, say, an integer, a whole number. You're not going to have 1.5 students. But you've made this property of your class object use a native data type. So you don't have to come up with your own. Name. Well, maybe that's a string. Description, that's a string. Grades it's suitable for. That's a set of numbers. Grades 9 and 10. Prerequisites. This could be a collection of classes. Now check that out. Now we got weird. We have a class, and we're saying one of its property is a collection of other classes. Well, wouldn't it be? What if you're studying physics 3? You would have prerequisites of physics 2 and physics 1. So you're using your own class, your own objects you're making in creating these appearance, these properties. You're going to build all of these things in very concrete ways. So you'll be able to look at this concept a bunch of times. All I'm really trying to illustrate is this. When we look at the 5 basic things and we look at variables, it's the entrance point to the language for figuring out how it implements certain really important things, not just the fact that it allows variables. Every programming language will allow variables. They're not going to force you to hard code things. But it shows you how to start learning the language. First, what are the built-in data types? Secondly, if I want to make my own types, how does it allow me to do that? How do I make new objects in this particular language? Now, we're going to learn all of that in JavaScript. But these questions remain the same. Any language you learn, it's one of the smartest places to start is, okay, what are the built-in data types? How do I make my own? Those types that I make are going to have both properties and behavior. How does this language let me make properties? How does this language let me define behavior? When you answer those, you're about 75% through learning how to use a language. And so it's a nice roadmap of how to learn. Any questions so far? All right, so let's jump up to the third one, which is control and branching statements or instructions. This is really key. One of the challenges, for example, that I see all the time on Twitter and lots of other places when they're trying to learn JavaScript is functions are kicking my butt. I can't figure out functions and how they work. And then you get even nerdier on it and they have these things called asynchronous functions. And like people get wrapped around a pole on this stuff. And I'm not saying it can't be challenging to learn. It really is. But understanding this next thing we're going to go over is the key to it. Now for this, oh, it's been a little while. I hope I haven't let my iPad completely drain. Oh, good. It's got juice. I'm going to share some stuff on the iPad. So give me just a minute. And really, this stuff is key. All righty. Notability, that's the one I was using. Okay, good. All right, so here's the concept we're looking at. Let's make a new one. We said that we have a starting point. This is the first instruction. And remember that over here in RAM, we have in our memory locations all the instructions we're going to do in our program. They're all just stored there, ready and waiting, and they're consecutive. So there's a couple of terms here. We're going to go from one instruction to the next to the next. This work of going from one instruction to the next is called a path of execution. Now, that's not something that you'll see in Outlander or Pirates of the Caribbean. Execution just means performing or doing instructions. In fact, for your principal program instructions, we call it the main path of execution. Now, at a certain point, you're going to have some sort of conditional instruction where there's two different options. For example, if your age is, erase that. If your age is greater than 21, you can buy cigars, greater than or equal to. And if it's less than 21, then no cigars. And from that point forward, you have a series of instructions. This is all in the main path of execution. But this is how a program works. It's very, very dumb, stupid, simple. Now we're going to add some complexity in a minute when we get to subprograms. Set that off to the side for now. When we look at these control or branching statements, they would seem to be extremely vital for any program because we build programs to make decisions for us or to automate decisions. Remember, when we're building a program, we're essentially putting into the computer something we could do manually if we wanted to. And most of the time, when we're making a program, we're replacing processes that were already being done manually, but we're using a machine to do them. And when we do things manually, we constantly have to make decisions. All the time. All right, let me make sure that my Twitch is working the way it's supposed to. Okay, good. So, control and branching statements are vital for implementing decisions. Now, they're not 100% required for a program. But if they don't have them, it's a slightly different kind of program. And we're going to get into a little bit of nerdy nuance. A batch or a script, these are two terms you're going to see. This usually means a series of steps you do one after the other that don't have any forks in the road. It's just straight on through from beginning to end. You can call it a program and nobody's going to be upset with you at all. But a really versatile program will absolutely make use of these control and branching statements so you can fork the path of execution. You can have deviations in it. These terms matter, especially when you're trying to learn a new language, and most especially when you're trying to learn functions or methods or subprograms, whatever we're going to call them in any language. So there's path of execution. Any questions about that? Good. And then there's control and branching statements, which shift the path of execution to one of two or more predetermined paths. By the way, one of the critical things about these control and branching statements is you have to create an actual path of execution for each option that you define, because a computer will only do what it's told. So let me make a tiny change here and ruin your program. What did I do? Anybody see what I deleted?
You removed the equal sign with the greater than.
Yep. How did I just broke the program. How did I break the program?
Because I think that would mean that they're kind of conflicted, the greater than 21 and the less than 21.
How do they conflict precisely? What is the exact case, the exact condition under which my computer program breaks?
I think it's because greater than 21. It's hitting 21 both times.
Well, what if I'm 25? Am I fine?
Yeah.
That's a really bad 25. If I'm 25, which way do I go?
To the left.
Good. If I'm 10, which way do I go?
To the right.
If I'm 21, which way do I go?
Oh, okay, yeah, that's when it would break.
Yep. I didn't account for every possibility in my control and branching statements. So when you're learning a new language, one of the things to learn is the nuances around these control and branching statements, exactly how to write them with this one thing in mind. How do I make sure I've accounted for all possible conditions that will arrive at this conditional statement? Here's the conditional statement. It's red. Sorry, here's the conditional instruction. It's red. If I'm going to have it evaluate a specific piece of data and then decide what to do, I have to make a path for all options Maybe if you're 21, you get you get some kind of, special sale offer because the first time you're buying cigars. I like cigars, leave me alone. So this is why control and branching statements are a good entrance point to learning a language. Obviously, for a program to be versatile, you're going to have to use a lot of them. And the nuances of how that language implements them, the types of control and branching statements available, this is really important to learn, especially if, and this happens all too often, the way they behave differs slightly from other languages you know. You can very easily make a mistake and not know it. Any questions? All right.
Kind of a,
yeah, go ahead.
Sorry, it's not necessarily right about that, but looking at the path of execution, is it something we're going to look at? Like, are you going to also teach us how to think so we can figure out what path we should take before reaching, for example, this fork? I saw you put some dots before.
Yeah, absolutely. Like you're talking about like how to think about the instructions to take when you arrive at that decision point.
Yes, exactly.
Absolutely. Absolutely. That's what we'll be doing. All righty. Put that up there. And turn it off so it doesn't kill my the battery. Okay, so let's go back to VS Code. So this is why the control and branching statements are so important. They let you control the path of execution. Learn the nuances of how your language does this. That's your entrance point right there, okay? Examples, what are some examples of control and branching statements that you guys have seen so far?
If statements.
If, then, else, others?
Switch statement.
Switch, good. Ellen, did you say something? Who was that?
I said for.
Yep, for loops, good. These are control and branching statements, excellent.
And while.
Good, excellent. There might be a few others, but these are the common ones you're going to see. Good, and in every language, they either have all of these or some of them. It isn't guaranteed they'll have all of them. Not every language has a switch statement, for example. And they might implement them a little bit differently. The other thing you'll need to learn how to leave the path of execution and return to the main path. Don't know why I did that. I hit the wrong keystroke. So, for example, when you're in a loop, and we'll see this when we start building loops, you've designed it to run a certain number of times. You might find that there's a time when you want it to stop running it. How do you do that? You want it to stop running before it was done. How do you do that? Learn those nuances about the language. All right, that's enough on control and branching statements. Because again, we're going to reinforce each of these 5 things in JavaScript. We'll get a lot more real. So here comes the one that's super important. They're all important. There's only 5 of them. Subprograms. Wow. What's a subprogram? Any ideas?
It's
like.
Go ahead, Ellen.
For it. Is it like I see something like steps, like small steps with tiny bit of programs that when they add up, you finally reach what you wanted at the first place?
Yeah, time program. Tiny, this is perfect. Tiny programs, and this is the important point, that you can call on from the main path of execution. This is what they are in fundamental nature. It can get a lot more complex. But they're tiny programs you can call on from the main path of execution. It's the best way to think of them as you're learning a new language. Why would you want to do these things? Why would you want to make these little teeny programs?
To make the code efficient, short.
Expand on what you mean.
So the program can run faster.
I don't know how it would make it go faster. Tell me what you think on that.
Was it the word bulky, less bulky?
But ooh, I like that. That's really good. Code is less bulky. That's a really good description. If I can spell it. Okay, good. Any other thoughts? Oh, go ahead.
We assign specific tasks to the subprograms.
Okay, you can have specific tasks done
assigned
by specific small
subprograms.
programs. Like that? Is that what you mean?
Yeah.
Okay, we're getting close to it. These things are all true.
Is it also so if you crash, you can just fix a tiny bit? And I mean, you can implement some unit testing and figure out where it crashed, and then you just have a small part of the program to fix instead of the whole thing that, you know, went crazy.
This is very close. Very close.
It's repeat actions.
Ah, this is the key. This is actually where it came about. So how this whole concept came about was early on when computer programming was in its infancy. We found that we needed, here's what we found. In a big long program where we'd start at the top and move all the way down to the bottom, there were certain sets of actions that we found ourselves doing over and over and over again. Let's say, for example, to go back to that nerdy example of doing calculations for a missile. Let's say at like 20 different points inside this program, we had to do derivatives, that nasty, gnarly mathematics thing that frankly, I understood once when I was 19 and don't remember much about since then. And there's a certain exact series of instructions to do derivatives, where you feed in the data and perform a certain complex math and you get an answer. What people found they were doing when they were creating programs is they would get to the first spot where they needed to do that, and they'd literally type out every single one of, say, 20 different instructions. And they get the output, and there's their derivative. A little while later, the program's bopping along, and they need to do another derivative. They type out all 20. A little while later, they have to type out all 20. It's the repeatable actions thing. Why is that such a bad thing? Give me thoughts on why that's bad. Or less than optimum.
Human error.
Human error, absolutely. What if you forget one of the instructions? Anybody think of another reason why it's less than optimum? It has to do with line 89 as well. There's some insight right in there. It's the flip side of it. It also has to do with one I should have written down from Sudesh about efficiency. let's say someone figures out a way to do that calculation, this derivative calculation, in 14 steps instead of 20. Now, let me tell you, in the early years of computers, when it was really expensive to make them and they didn't operate very fast, if you could reduce something that previously took 20 steps to only take 14, and especially if you had to do that same thing 20 different times throughout the program, that was a significant improvement. But now you've got to go back and find all 20 places in the code where you had that series of instructions and change every single one of them. Again, with risk of human error and with the waste of time of presumably highly paid computer programmers. This is why DRY, don't repeat yourself, is an absolute mantra, a slogan, almost a law in computer programming, because we did it wrong at first. And by the way, I don't know if you all know this, but in the early years of the computer industry, computer programs were completely not where it was at. It was all about bigger and better and faster hardware. People paid very little attention to computer programs. And it wasn't until like early 70s that people really started to treat the program itself as a first-class citizen. And a lot of this early thought work was done in what's the smartest way to put programs together and what's the smartest way to create a language for a given type of program. That's when you'll find a lot of the really important work being done. And around about that time is when this whole concept of don't repeat yourself came to be. So this is why subprograms are a vital part of a computer program. It's because it's very rare to have any program where you aren't going to have at least a few repeated actions. Each time they're done, they might have different inputs, but they're going to do the same work over and over and over and over again. And so this is why subprograms are so vital. Without them, you have bulkier code. I really liked that, okay? Much longer, huge sections that repeat themselves that are difficult to write and difficult to maintain and difficult to improve over time. So that's why we need subprograms. Any questions on those concepts? Okay. All right, so it's 8:03 Pacific. I wanted to go till at least 8:30. Okay. You guys want to just power through and go without a break?
I'm good without a break.
Okay.
Yeah, I'm okay.
Jason? Okay, good.
That's good.
Awesome. Okay, good. All right, so let's look at what these look like visually, okay? And I want to visualize it because picturing this in your head is going to be really valuable when we start learning about JavaScript functions, or frankly, how subprograms are done in any language. So let's go back to this little sketchy sketch. And let's look at subprograms. Now, the way to start with this is to realize that they are programs all in their own right, which means they have a starting point, they have an ending point, they make use of variables, they make use of control and branching statements, and they can even call other subprograms. But we'll look at that part later. For now, just know that they really are computer programs. Here's how they work. You have your main program, and it has a starting point, and it goes along and it does instructions and does instructions and does instructions. Now I'm going to, and then you have an end point. What I'm going to do is I'm going to change the color on some of these to, oh, green isn't very visible. let's make it red. Each one of these is a point that represents a series of exactly identical instructions. We have 3 of them. And so our program is longer than it needs to be. It's error prone, and it's hard to change it after the fact if we find a better way to do whatever those identical steps are. So we want to create, I'm going to pull this stuff out, pull it out or extract it, these instructions. And let's say this little red dot here represents 5 instructions. What we'll do is we'll write those down, package them up, and typically we'll give them a name. I'm going to call it subprogram number 2. That's silly. Subprogram number 1 because we only have 1. Now, what you do is you change your computer program instructions. And right here, where you had this dot, and this dot, instead, you have a special instruction where you call subprogram number 1. You do that 3 separate times. And that is an almost universal word that's used in almost all languages for using a subprogram. You call on the subprogram. Now, remember our path of execution. This is what it looks like now. Here's our start. Here's our end. And it looks like this. Every single one of these little detours is where the main path of execution was transferred to subprogram number 1. When subprogram number 1 is done, remember, it has an exit like any program. The computer's focus returns to the main path of execution. In fact, I'm going to change the color here. Main path of execution is red. This is actually how your computer keeps track of what it's doing. It will literally get to the first time that we call on subprogram number 1, and it'll remember what instruction it was at and what's the next instruction in the main path of execution. And it says, hey, subprogram number 1, can you please execute? And subprogram number 1 does its 5 steps. And then the last step is the exit. And it says, okay, I'm done. And the main program, the CPU says, oh, that's right, here's the next instruction. And it just starts doing the instructions. And it hits another point where we call on subprogram number 1. And the computer keeps track of where it was and what's the next spot and calls on subprogram number 1, and it does the same thing. What we're doing is we're taking the focus of the CPU and we're transferring it over to a different program temporarily. And when we're done with that program running, we come back to the main one. Any questions so far? Now I want to point out that we're still only doing one thing at a time. All right, now let's add a little bit of nuance. Let's look in detail at the point where we hit the instruction that says call subprogram number 1. And here's subprogram number 1. Think of it as a box. In fact, I'm going to make it black because you can view it as a quote unquote black box. As far as the main program is concerned, it has no idea how it does what it does. All it knows is, 1, call it. 2, give it what it needs. 3, and this is optional, take what it gives you. And 4, keep going where you left off. Other than that, it has no idea what's going on inside here as far as the main path of execution is concerned. So it'll call subprogram number 1. Oh, that was a mistake. I changed to eraser. It'll call subprogram number 1. Sometimes subprogram number 1 needs some data to do its job. And sometimes subprogram number 1 has some data to return. Not always true for either case. What is true is that you have to call it, and when it's done, you keep going where you left off. Those things are always true. Questions so far? Okay, good. Then let's expand on calling it, and we give it data that it needs. And here's subprogram number 1. And then inside it, it creates a result of its work. And it sends that result back to the main path of execution. Here's your main path. So we stop right here, call on subprogram number 1 while giving it the data it needs. Subprogram number 1 does its work, which includes creating something that's a result. The subprogram sends that result back to the main path and also says, hey, I'm done. Presumably, the main program is using that result for something. So now let's start to look at some terminology. It's not constant, sorry, it isn't consistent, this terminology across every language, but it's pretty common. The data that you send to the subprogram is called parameters. And the data you get back is often called the result or the return. Those are the 2 words you're going to see. You can see why they would call it a return, because it's what is returned back to the main path of execution. Questions so far? Okay, good. So what are the various terms for a subprogram that you guys have encountered in different languages?
Functions.
Function, good. Method. Subprogram. See if I can actually spell that. There might be others, but those are the most common ones you're going to see. Now, this part is pretty important. Depending upon who designed the language, they may have very important distinctions between these words, and you need to learn what they are. But the central concept will absolutely be the same from one language to the next. And the central concept is, I have work over here that I need to be done on a repeating basis. My main path of execution can call on that work to be done. And when the work is done, it'll inform the main path of execution. Sometimes I need to give that subprogram information. Sometimes I don't. Sometimes that subprogram, when it's done, returns some information. Sometimes it doesn't. Those concepts remain the same in all computer languages. And so your task when you're learning a new language is to see, one, what do they call subprograms?
Is there something else?
No, Siri, there isn't. What do they call subprograms? 2, if I want to give them data, how do I do it? 3, if I want them to return data, how do I do it? There you go. As you examine that area for any language, you have now added one of the most important pieces in the toolbox for using that language effectively, which is you can practice, don't repeat yourself. You can design repeatable programs. Later on, if you find a smarter way to do it, you can change the program a little bit, and every single place that you're using that program receives the benefit of your change. You see how it's a really vital part of learning a new language. Cool. How are we doing? Any questions? Okay, good. All right. Now we're going to move on to the last one. You might remember what this last one is.
Exit.
Good. Exit point. Now, just so there's a little bit of notes here under subprograms, main path of execution calls them. It may or may not need to give them info. They may or may not return info. When they are done running, the main path of execution continues where it's left off. Good. So now let's get down to this exit point. Why do I care? Why do I care that a program has an exit point? The program's over. Who cares? Any thoughts?
It has to stop at some point.
Okay, so it stopped. What's going to happen?
It needs to give you something.
Okay, if it's still giving you something, then the program's still running. Let's say it gave you everything you needed and the program is literally turned off. Like we reached the last instruction. Go ahead.
Is it so it can reallocate the memory it was using or something for other things?
Spot on. That's exactly what it is. So CPU allocates resources. They are in RAM. What is in RAM while a program runs? Any thoughts?
Stored values.
What?
Values.
Yeah, variable values, right? So variables and their values. Let's get a little more detailed. User created data. This is the objects that you made. Let's say your program was running and you were working on 5 different classes from our earlier example, a math class, a physics class, an English class, whatever, right? Well, all of those objects are being maintained in memory by the computer as you're working on them and changing things. Now, eventually you'll probably save those changes to a database and then you can turn the program off. But while the program is running, you're taking up valuable RAM, valuable memory space to hold all that information so your program can quickly access it and change it. And here's another super important one of what's in RAM, the actual program. They have to be somewhere. You're not going to leave them down on the hard drive because your program needs to look and almost instantly see what the next instruction is. Your CPU doesn't have time to wait to reach down onto the hard drive, retrieve the next instruction, and then execute it. No, it's going to take all of your instructions and chunk them, store them right in a big section of RAM and use up all that RAM. And then it's going to start going through and doing all your instructions one after the other. So your actual program, the instructions itself, are taking up RAM space. So when you no longer need the program, get rid of those resources. Free them up. That's exactly what he was saying. Now, why do you care about this? Not all languages do that in the same way. Not all languages will free up those resources in the same way. For some languages, especially the lower level languages meant for really, computing tasks that have a very small amount of available memory, there might be very unique particulars to how they manage the memory while they're running and what they do with the memory when they're done. It isn't all of them. It's really not common, but you should at least look into it. You should look up memory management for language X, or freeing up resources after program in X language closes. And you'll find out if there's some nuance. Now, admittedly, this one it really doesn't come up that often, but it's something to know. And it's something that a computer program has to have. There's got to be a final instruction, some way to tell the operating system, hey, we're done with this program. Whatever it is you're meant to do, you can go ahead and do it. Questions about that? Okay, cool. Well, what we have here is the blueprint for how we're going to look at studying JavaScript. We'll look at, when you're creating a program in JavaScript, how does the CPU know where to find the first instruction? That's actually more important than you would think when you're learning a new language. Then we're going to look at how do we declare variables and what are the different types of data that are built in. And then we're going to expand on that a little bit. How can I make my own types of data, my own objects? Then we're going to move into these control and branching statements. Which ones are available in JavaScript and how do they work? Are there any weird nuances? We're going to look at the question of like, back down here, control and branch. Like, let's say I'm running a loop and I want to leave it early. How can I do that? How does that work? And finally, this is the fun part, we'll look at subprograms. In JavaScript, the word used for them almost all the time is functions, but JavaScript has a difference between a function and a method. They do actually mean separate things, and we'll explore that. The basic principle, totally the same, but we'll look at the nuances there. And finally, we'll look a little bit at exit point. It doesn't matter too much in JavaScript, but we'll look at it. So that's our blueprint for how we're going to study JavaScript. Any questions? Cool. Now, we are going to be meeting again in 2 days. I'll tell you though, armed with this information, I would have no problem with you guys diving into some of the introductory JavaScript materials you may have used in the past and looked at, and seeing, well, how does this material look from this point of view? How would I figure out where the entrance point is? Eric is saying there's always a first instruction. How do I find that out for a program? You can start studying on your own. I have no problem with that. In terms of technical homework, nothing right now. We're going to meet in 2 days. If you're a little bit behind on the homework, most of you turned that in. Go ahead and try to get some of it done. Okay. And that's it. That's what I have for you. Anybody got any final questions or comments before I give you back 5 minutes of your day? Okay, cool. Yeah. Thank you all for participating. This is a foundational element, and I hope it helps as we dive into. Oh yeah, Ellen, please.
Would you mind to share with us the file you just took also?
Yeah, absolutely. In fact, I'm going to take it and I'm going to put it inside our 5 Live thing. So yeah, let me do that right now, and I'll share it with you. complete with typos. Yay. Oh, interesting. Let's see if it'll send. Yeah, it won't work because I included a pound in the name of the file, which is an absolute mistake. So let me close it and then rename it. Give me just a second. Oddly enough, if you have the pound symbol as the first name of a file, it doesn't work. Who'd have thought? All right, there it is. It's in chat. Go ahead and grab it before I shut down the Zoom meeting.
Awesome, thank you.
Excellent. Oh, it took a little while to send. Anybody not have it? I should have sent that in Discord. Duh. Okay, cool. Awesome. Thank you all very much. I will see you all in 2 nights, and we'll start writing some JavaScript code.
Thanks. Have a good night.
Thank you.
Thank you.
Thank
See you
you.
guys.
Have a good time.